So I think my audio is on, right? It is. Okay. Uh, so what is this thing? So the last time when I was solving Erodo, right, that book, I encountered a question which, yeah, it involves a differential equation which I couldn't solve because it was the differential equation was basically this thing that your acceleration, the acceleration in the x direction that's given by negative of some constant times the x upon the r power 3 value, right? So r is just x square plus y square power 1 upon 2. So this is just x upon r cubed. So yeah, that's how uh, this is going. All right. And then also this extra term, so minus b times the velocity in the x direction times the magnitude of the total velocity, that is ux square plus uy square to the power of 1 upon 2, right? So that thing. And then similar stuff for y. And b is a constant, a is a constant. I have given them over here. And they gave us the condition that b is just very small. They didn't give us anything else. So yeah, it took some tries, but finally I have a good setup right now. So this is all the program that I will use to graph out what the path would be. So t over here, this thing, right? This is the time till which we are going to run this program. So it won't be the actual time. It's the time that would be if the motion was carried out in reality, which we cannot carry out because we don't have actual planets on our hand, right? You get the thing. So t is just the time till which we are going to do this thing. And n is the number of divisions that will make in this time to get our delta t's. So delt, that's basically t upon n. And then using kind of like a recursive process. I know. This is not exactly recursive in programming terms, but in uh, right, to solve this differential equation, what I'm basically doing is at every step, I'm just changing the ax, ay, the xy, and ux, uy values depending on the previous information. So, right, that is what the differential equation basically says us to do, right? So, yeah, I'm just doing um, whatever is done in reality, but at a much more, uh, let's just say, doable level, right? A level where we got a lot of errors going on because I cannot have infinitesimally small time intervals, but still I can try, right? I can make them as small as this computer can handle, right? So actually you are missing 3 zeros over here. But what I want to do is show you that as we increase our accuracy, this graph actually turns out to be the same graph as we keep on going. And that would basically prove that the graph is like that it's not, uh, right. That's not how the graph looks for just n equal to 10,000. It would also look this for 100,000 or something like that. If I can prove that, then that would basically mean that that graph is what resembles the actual path that you would have, right? And then you got this commented out stuff, which I will use later to actually show how the object moves. But right now, let's just run this program. So it will give us an image when we run this thing. So let's do it. It will take a lot of time. So yeah, you will have to wait. Ooh, that's not responding. What? No, it must be responding. Don't tell me it's not responding. Okay, it is responding. Fine. Right. So n equal to uh something like 1,000 or whatever. That gives this kind of a graph, and this is not nice because this is not the graph that would be for, well, let's just say, the higher end values. So this is a very, very, let's just say, wrong graph. And then as we increase our n values, we'll get better graphs. So let's do that. And also actually close this really fast because Right. So we'll make this better by increasing this accuracy. Now let's run this thing. Just just don't freeze right now. Oh God, this should just not freeze. If it doesn't freeze, then we will be good to go. Okay. I swear when I ran this without the recording, it ran perfectly. So it should right now as well, I think. Okay, so this is for an the next level of accuracy. So this is getting somewhere. It looks elliptical and everything, right? Much better than what we got previously. Let's keep on going. So we'll increase this by putting another zero, right? Yeah, so control S. Now you got like what? A million, right? Let's run this thing. Now it's gonna take much more time because we have increased this. So it's exponential increase, and that's why the time required will be linearly increasing. And after some time, it will just run out of juice to carry on the computation. Yeah, we'll keep on doing it till that moment, and when that happens, it happens. Whatever. If we are lucky, I'll get to show you how this actually works. So yeah, this is how it actually should be, I think. So let's increase the accuracy once more, and then if you get the same kind of graph, then perfect. That will basically tell us that it is the way that graph should look. Okay. So we'll make n higher once again. This is kind of scary because I've never actually went to this big n value, but let's do it now. We'll see what happens. Control S. Now let's run this thing. Right. I have no idea what's going to happen. Okay, it's doing the thing. At least it's responding. Come on. Yeah, you can do it, don't you? Right, come on. We are so close to proving that it's actually the graph. Okay, come on. You can do it. Uh, how long is this going to take? I have no idea. Uh, yeah, I mean, I didn't say it's actually linearly, right? So the time required is gonna increase linearly, right? So, mhm. Wait, I don't think, was this like linearly or what? Huh, I don't remember the thing. So 10 power something, the natural log of that is like n natural log of 10. Hey, that's not linear at all. Okay, okay, so the time required is not linear because it's taking a lot of time. I thought it would like, it would just, yeah, that's weird. So how long? How long do we have to wait? I've never tried it at that n value, so ooh, look how fast this is blinking, right? Oh yeah, here we go. So as you can see, this graph is very much the same graph that we got the last time. And what does that tell us? That tells us that the last time's graph was also correct, right? And both of these graphs resemble each other. That just means both of them are correct. That's all you need to know. So one thing to notice is that uh, these loops are almost like these are almost elliptical, except that these are actually spiraling down. So yeah, you can think of it like, okay, in every single turn, what happens is that it goes like this and it comes back. So it was kind of an ellipse, and then it once again goes like inside and comes back. It was kind of an ellipse, except that you have this shift. So okay, we don't want that right now. Okay, yeah, I just close this thing. So yeah, I want to kill this program because so what we basically proved is that even for this accuracy, it would have given us the same graph and the correct graph basically. So we'll actually use this accuracy in that case. And now I can uncomment this thing and show you how actually the thing moves. Okay. So the main point is that just using energy changes. So how the energy of this motion is changing. Just using that, actually, I can figure out how the minimum distance is changing for these kind of elliptical orbits, right? So these are elliptical orbits that are getting smaller and smaller in their Rmax values, right? So how does that change? If I can show you that thing, you are basically done, right? Yeah, exactly. Uh, okay. So let's do the thing. Let's actually show you how the point moves. So next time I'll get this kind of question, I will be able to solve this because I'll just apply dE upon dt and then use the fact that E is just negative gm upon 2a squared, right? And also the fact that eccentricity is almost the same. All of those ellipses were almost the same, right? So you can assume eccentricity is not changing that fast, and yeah, that's enough, right? That's enough information to show. And as you can see, like this distance versus this distance, it's actually a big deal. Yeah, this changed by a big factor, right? So a kind of did change, but look at this eccentricity, the eccentricity of this thing and eccentricity of that. It's, yeah, I mean, it's very much the same because it's basically like, okay, how far away is that? Should I even say what that is? Well, whatever. Actually, no, maybe we should not say that electricity didn't change. It did change. Just it was like changing gradually or something, right? The main point, the main takeaway is that, um, right, that your orbits, orbits in a short time span are almost elliptical, right? I'm saying orbits, it's actually an orbit because there's only one orbit. But yeah, that orbit for a short time span is elliptical, and then for a large time span, it does this spiral motion. That makes sense? Right. And now I can finally solve that question. I didn't know actually I would have to, basically make a program that solves differential equations because that's what I'm doing right now. I searched for something that solves differential equations and they told me that Python can do it. They have a library for this thing. But I thought, well, whatever. I won't use the library. I'll just use the basic concepts that the differential equations work on. And boom, I have this thing now. And of course, it's very slow in comparison to what they are able to achieve. But still, it's something, right? Starting from scratch. And yeah, just look at spiraling down. How beautiful is this? All right, let's stop this. This is crazy. Okay. Yes, I want to kill the program. So that's it. Uh, I think this was convincing that you can just use, the rate of change of energy stuff to get the thing done, right? If that was convincing, nice. So that's it. I'll see you in the next video.